So, hello everyone, welcome to my YouTube channel. So, in this class, I will discuss about the metal carbonyl organometallic compound complex. So, metal carbon monoxide is one of the most important ligands in the organometallic chemistry. So, here this it can donate or coordinated to the metal center via this carbon atom, and this bonding of the carbonyl to the metal is highly sensitive to the electronic effects on the metal centers. That means the electron density on the metal center will affect this carbon oxygen bond order. So mainly these carbonyl ligands stabilize the low oxidation state of the metal, because low oxidation state means if the low oxidation state there is a more electron density to the metal center, it will favor the back bonding to metal to carbonyl. So that's why the carbonyl is stabilized with the slower oxidation state of the metal center. So first we will discuss about the structure and bonding of this carbonyl ligand. So this is the MO diagram of this carbonyl ligand. So carbonyl ligand basically is a pi acidic ligand, and it's from this molecular orbital diagram, the HOMO is a of carbonyl is a sigma orbital, and it has two lone pair. So this HOMO is the energy of this HOMO orbital is close to the carbon energy of the carbon atom. So that's why the carbonyl is donating coordinated to the metal via the carbon atom. Means the lone pair is mostly on the carbon atom. So that's why it donate via the carbon atom. And here the LUMO of this carbonyl is a pi star orbital. It also is the closer energy to the carbon atomic orbitals compared to the oxygen atomic orbital. So it will affect the electron density from the metal center to this pi star orbital. So that's why the carbonyl is a strong sigma donor and pi acceptor ligand. So this is the orbital diagram of this carbonyl molecule. So in the carbonyl molecule, both C and O are considered as a sp hybridized, and bond order of this carbonyl molecule is 3. So here total sp hybridized means one sigma bond, two pi bond is formed. So one sigma bond is formed from the singly occupied this sp orbital of O oxygen and sp orbital of carbon. A sigma bond formed between these two, and the pi bond is formed between the singly occupied pz orbital on the carbon atom and pz orbital on oxygen atom. They will overlap and form the pi bond. And second pi bond is formed between this filled p orbital of oxygen. We donate electron to this vacant p orbital of carbon. So second pi bond is formed after donation to the lone pair of OP p orbital of oxygen to the vacant p orbital of C. So that's why these two pi bond and one sigma bond is formed between this carbonyl molecule. So here, if for formation of the second pi bond, the transfer of electron to the oxygen to carbon atom is happened. So that leads a polarization on this molecule. That means there is a slightly negative charge on this carbon atom and positive charge on this oxygen atom. which is almost cancelled out by the partial C polarization of carbon. There is a positive charge on carbon and negative charge of oxygen. Because of the higher electronegativity of the oxygen, which is cancel out this polarization. So overall, this carbonyl molecule has net dipole moment close to 0. So it is a neutral. So that's why it is a neutral ligand. It is a L-type ligand. So now I will discuss about the bonding of CO ligands to the metal center. So CO is basically a strong sigma donor and pi acceptor ligands. So it will donate electron to the metal center via carbon atom. So its HOMO is a pi star, is HOMO is a sigma orbital and LUMO is a pi star orbital. And so it will, so this is the MO diagram for this metal carbonyl bond formation. So here this is the HOMO of carbonyl, this is the LUMO of the carbonyl, and it will, there is a bond between the donation of the this lone pair to the metal vacant d orbital, and there is a electron donation to the field metal orbital to this LUMO of the carbonyl. So this is the electronic structure, orbital electronic interaction of this between the bond formation, this sigma bond formation come via this electron donation to the empty d orbital, and this pi back bonding is formed between this field metal d orbital to the empty pi star orbital. So CO is can donate the electron to the metal center and expect the electron to the from the metal center. So there is a back bonding between this metal and carbon. So the extent of back bonding means the how much back bonding is formed is totally depend on the electron density of the metal. So we, if the metal electron density will vary, so that will vary the extent of pi back bonding. If the metal is more electronegative, that will donate more electron to the pi star orbital of CO, that will decrease the bond order of the CO molecule. So that will identify by the IR stretching frequency of carbonyl molecule. So now I will discuss about the binding modes of the CO. So CO can binding in two phases. One is terminal and one is bridging. So in terminal mode, CO bind, one CO is bind to the one metal center. So it's a linear fashion. And in the bridging, the one CO is bound to the more than one metal center. So here this CO is bound to the two metal center. So this is a mu2 bridging, and here this CO molecule is bound to a total 3 metal center. It is a mu3 bridging. So we can identify this mode of donation or attachment of the metal center to the carbon by the IR stretching frequency. So here the IR stretching frequency of free CO is higher compared to the terminal bridging, and bridging has low IR stretching frequency compared to the terminal CO molecule. So mode of the carbonyl will be identified by the IR stretching frequency of the carbonyl molecule. So extent of pi back bonding is strongly depend on the electronic density of the metal center. So how the metal, how much back donation is formed, back bonding is formed, that will totally depend on the electron density of the metal center. If electron density on the metal center is less, so there is less amount back bonding, so there is a higher bond order compared to the if the back bonding is higher. So there is one example. So here total this 6 molybdenum carbonyl complex. So here from down up to down, this stretching frequency of the metal carbonyl stretching frequency is decreases. So that means with going down, there is a more back bonding, more electron density of the molybdenum. So that's why the stretching frequency in decreases. So because the PF3 is strong electron accepting ligand, so due to the more electronegativity of the phosphine, electron of fluorine, so it will accept more electron to the from the metal center compared to the py3. So that's why for this ligand the electron density of the molybdenum metal center is less, so that's why there is no such back bonding. So that's why the stretching frequency of the carbonyl is higher compared to the other. And down to the group, there is more electron density of the molybdenum, so more back bonding. So here the stretching frequency is decreases. So now I will discuss about the synthesis of the metal carbonyls. So metal carbonyl can synthesize in various ways. So one is direct carbonylation. So direct carbonylation means we can react the metal and the carbon monoxide and the carbon monoxide gas that will form the metal carbonyl bond. So this method is applicable. So synthesis only few carbonyls is a classical example of which discovered by the scientist Mon in 1890. It has been utilized in the refining of nickel as well iron. So here this nickel metal is react with this 4 molecule of CO that will pour this nickel CO whole 4. And similarly the iron will react with 5 molecule of CO that will form this FeCO whole 5. And another method is reductive carbonylation. So reductive carbonylation is the most commonly used method for preparation of binary metal carbonyls. So here for this reaction, a reducing agent such as a aluminium, sodium, zinc, alkyl aluminum or Grignard reagent are used in this reaction with metal halide or acetate with carbon monoxide at higher pressure and temperature. So main difference of in this direct carbonylation, they use a direct metal with this carbonyl, but in this reductive carbonylation, here the metal halide precursor is used, so that will react with this aluminium or the sodium. This is used as a reducing agent that will react. Here the chromium chloride with aluminium, 6 equivalent of carbon monoxide with react with this and form CrCO whole 6. Similarly, this MoCO whole 5, here the sodium used as a reducing agent, so that will react with 6 molecule of CO that will form MoCO whole 6 and NaCl. So and also in the case of metal oxide, the carbon monoxide itself as a reducing agent and gets converted to carbon dioxide in the presence in this process, and the reaction conditions are relatively more drastic for such reaction. So here this osmium oxide OSO4 and carbon monoxide, which is itself as a reducing agent in presence of methanol 125 degrees centigrade temperature, it forms this OS3CO whole 12, and this carbon monoxide is converted to carbon dioxide. And another is rhenium. This rhenium oxide is react with this carbonyl to form this this metal carbonyl complex and 7 molecule of CO2. So mainly in these two processes, the metal carbonyl bond is formed. So next we will discuss about the reaction of metal carbonyl. So how this metal carbonyl compound is react, what type of reaction they can goes. So first one is the activation of the metal carbonyls. So Lewis bases or olefins are arranged at they say the some ligand which can thermally substituted on the metal carbon. That means this if there is a total if that means the metal carbonyl this ligand is substituted by another neutral ligand. That means that is olefin or arenes, that one. But the complete substitution of all carbonyl groups is rarely accomplished. So one method that is usually adopt is the activation of metal hexacarbonyl by intermediate introduction or relatively more labile ligand that is replaced later by the other ligand under mild condition. So here the activation of metal carbonyl one reaction is this chromium hexacarbonyl complex react with the THF to form this intermediates. So here one carbonyl is substituted by this THF ligand, which is a labile ligand. And another reaction is this chromium hexafluoride is react with this moiety with from these intermediates. Here total 2 carbonyl is substituted and 2 pi bond is formed between this metal and this olefin bond. So second reaction is the disproportion reaction. So multi-metal carbonyl can undergo the disproportion in the presence of suitable ligands open leading to the carbonyl anions. So this is the metal carbonyl moiety that will react with this pyridine and form this metal carbonyl anion species. So that's why here it is a neutral and here it is a +2 oxidation state. In the manganese here is a -1 oxidation state. So here this proportion reaction happened of this manganese to this +2 and -1 oxidation state. So that is one important reaction. The metal carbonyl can undergo the disproportion reaction. So next the nucleophilic addition of the carbonyl. So here the carbon atom of the carbonyl molecule is electron deficient. So nucleophilic can attack to this electron deficient carbon atom of the metal coordinated carbonyl groups. So this nucleophilic addition, so it is this reaction is normally called this Haber base reaction. So here Fischer carbene can be prepared by addition of this alkyl lithium, this RLi to the metal carbonyl followed by the methylation. So here this tungsten moiety, here the carbonyl C is electron deficient and RLi it will give R minus as a nucleophilic. So it will attack to this carbon atom from this intermediate and we substitute methylated to form this carbene moiety. So nucleophilic addition happened to the metal carbon atom of the carbonyl moiety. So next the another class of reaction is the electrophilic addition to the oxygen carbonyl oxygen. So carbon atom of the carbonyl moiety is electron deficient, but oxygen molecule atom is the nucleophilic nature. So electrophilic can attack to this oxygen molecule of this metal carbonyl compound. So then one type of reaction, Lewis acid such as Al83 can attach to the oxygen end of the coordinated carbonyl group. Only bridging carbonyl groups are nucleophilic enough to undergo this reaction as per the neutral metal carbonyl had considered. Addition to the electrophilic become more facile with anionic carbonyl metal. So here this is an example of the electrophilic addition of this carbonyl oxygen atom. So here this Al83 is the electrophile, it attacks to the nucleophilic oxygen atom to form this ADAC. So this is the electrophilic addition of the carbonyl oxygen. So another class of reaction is carbonyl anion formation or carbonyl cation formation. So carbonyl anion formation are formed by reduction or the reaction with the strong nucleophilics. So these manganese carbonyl precursor react with two equivalent of sodium that will form this carbonyl anion ligand. So here manganese zero oxidation state, and here it form MnCO whole 5 minus. So it is in, so it will form this carbonyl negative attack. So here also the cobalt carbonyl species will react with two equivalent of sodium atom, and from this carbonyl anions adapt. So another one is the carbonyl cation preparation by mostly the oxidative carbonylation. Lewis acid in anhydrous HF or superacid such as HF-SbF5 along with the external oxidant are found to be the ideal for realizing carbonic cations. So here FeCO5 react with the XeF2 or SbF5 to form this metal carbonyl cation adapt. And for this manganese also here this metal carbonyl adapt is formed. Next, we will discuss about the Coleman reagent. So Na2FeCO whole 4 is called as a Coleman reagent. This has important application in organic synthesis. So organic halogen compound can be functionalized in many ways via the reaction with this Coleman reagent. So here Na2FeCO whole 4 react with this halide to form this adapt, and there and next one molecule of CO can react with this intermediate to form this intermediate. So after that from this we can functionalize and this organic halide. So if in presence of acidic proton it will give this aldehyde moiety, and in presence of X2 means it will form this RCO whole X moiety, and in presence of another molecule of organic halide it form this keto moiety, and in presence of oxygen it will convert it to the acid moiety. So Coleman reagent has important role in this organometallic organic synthesis. So next class of reaction is the migratory insertion of carbonyl. So ability of the metal carbonyl, especially the metal carbonyl anions to undergo migratory insertion, has been utilized in organic synthesis for preparation of acyl substituted metal carbonyl. This is a good precursor for host of the carbonyl containing organic molecule. So migratory insertions means this is MnCO whole 5 Me. So here one molecule of CO inserted between the alkyl manganese bond to form this intermediate in presence of high pressure of carbon monoxide. So this reaction is called the migratory insertion of the carbonyl. So that means this one molecule of carbonyl in inserted between this metal alkyl bond. So we can use functionalize this moiety, which has very important role in the organic transformation. So next was the oxidative decarbonylation. So carbonyl metal halides are prepared via this oxidative decarbonylation and this is a good reagent for reaction with methylated reagent. In addition, substituted metal carbonyl can be converted to the metal oxide by oxidation decarbonization. So here this manganese precursor will react with this iodine to form this metal carbonyl halides. Similarly, this iron FeCO5 react with this iodine to form this metal carbonyl halide moiety. And last one is the photochemical substitution reaction. So photochemical substitution are the most commonly photoreaction in the organometallic chemistry. Kinetic studies show that the rate constant of the dissociation of one CO unit which proceeds the entrance of the new ligand is increased upon the photochemical excitation of factor of 10 to the power 16. So here this tungsten CO whole 6, it is react with the PPH3 in upon presence of light, which to form this tungsten CO whole 5 and PPH3, and one molecule of carbonyl is dissociated. So here the PPH3 is substituted one molecule of carbonyl, and also the FeCO whole 5 react with this 1,3-butadiene. Upon photoradiation, two molecule of carbonyl is substituted to form this FeCO whole 3. So this is the overall idea about the metal carbonyl bonds. So thank you. So now I will discuss about the some problem on the metal carbonyl or metallic compound. So first one is the vanadium CO bond distance in VOCO whole 6 minus and PCO whole 6 are 1.93 and 2.0 Armstrong respectively. Justify the difference in the bond distance in this compound. So vanadium is a group 5 metal. So its electronic configuration is 4s2 3d3. So in VO whole 6 vanadium oxidation state, VCO whole 6 vanadium oxidation state is 0, and VCO whole 6 whole minus vanadium oxidation state is -1. So in VO whole 6 there is more electron density on the vanadium metal center compared to the VOCO whole 6, because VOCO whole 6 minus is a more electron dense. So from previous class we know that if the metal has more electron dense, then there is more back donation from metal to carbonyl pi star orbital. So in the case of vanadium CO whole 6 minus, there is more electron density, so it will favor more back donation to the carbonyl pi star orbital compared to the VO CO whole 6. So in case of vanadium CO whole 6, as there is more electron donation, so vanadium carbon atom bond length will be bond order will be increased. That means this vanadium carbon bonded is more pi bond type character compared to the VOCO whole 6. So as the VOCO whole 6 vanadium carbon bond length bond order will be increased, so the bond length of the vanadium CO whole 6 is shorter compared to the VOCO whole 6. So next question is the what happens to the stretching frequency of CO when CO gets connected to the BH3 or nickel CO whole 3. So we know that CO is a strong sigma donor ligand, and it will eject electron to the pi star vacant pi star orbital of this sigma star pi star of the CO. So here for the NiCO whole 3 case, NiCO whole 3 case, nickel has electronic configuration of it is a group 10 electron configuration and 4s2 3d8. So for the nickel case, when carbonyl is coordinated to the nickel center, it will donate the electron to the nickel, and nickel also donate its electron to the pi star orbital of the CO. So that means there is a back bonding between the nickel and CO. So as back bonding is favorable, so in the carbon CO bond order will decrease, and so the stretching frequency will decrease compared to the free CO in case of nickel CO whole 3. While in case of BH3, it is a Lewis acid. It's Lewis acid, so at its needs electron. So when CO coordinate to the BH3, the only CO will donate the electron density to the boron atom, but boron atom have no electron to donate the CO. So for this case, the back donation is not happen. So here the CO bond order will be increased, and this CO stretching frequency of the CO is slightly increased compared to the free CO. So the stretching frequency of CO BH3 will more compared to the free CO compared to the CO nickel. So this is the order of the stretching frequency when CO coordinated to the BH3 or CO coordinated to the NO3. Because of the background in the case of nickel, there are back donation, so stretching frequency will decrease, and in the case of BH3 there is no back donation but only pure sigma donation from CO to BH3, so it will increase compared to the free CO. The next problem is, which one of the following given complex undergo ligand substitution reaction faster with PPS3 and why? So vanadium is a group 5 molecule, group 5 atom, so its electronic configuration was vanadium, its electronic configuration of 4s2 3 valence electron configuration 4s2 3. So in CO whole 6, so vanadium CO whole 6, it is in the vanadium oxygen state, total 0, so total electron count, and for vanadium it will donate total 5 electron, and to 6 kilo total give 12 electron, total 17 electron. But in case of vanadium CO whole 6 minus, total electron will be 6 plus 12, total 18 electron. So vanadium CO whole 6 minus is a 18 electron complex, and VOCO whole 6 is a 17 electron complex. So So the ligand substitution reaction mechanism was different for this case. VOCO whole 6 is a unsaturated, it is 70 electron, so it will goes via ligand substitution via associate mechanism. But for the VOCO whole 6 minus, it will be saturated, it is 80 electron complex, so it will go via dissociate mechanism. But for rate of the ligand substitution reaction with PPS3 will be faster for VOCO whole 6, because for VOCO whole 6 minus there is more electron density towards electron density on vanadium because it's a negative charge. So here more back donation to the vanadium to carbon. So here vanadium and carbon bond is more stronger compared to the VOCO whole 6. So the rate will be slow for VOCO whole 6 minus and rate will be high for VOCO whole 6. So final answer is rate VCO whole 6 will be greater compared to the VCO whole 6 minus. So next question is vanadium CO whole 6 readily react to its the sodium to give NaVOCO whole 6. Why? So V is a group 5, so it electronic configuration is a 4s2 3d3. So vanadium CO whole 6 has total 5 plus 12, total 17 electron. So vanadium CO whole 6 has total 17 electron. So according to the 8 electron rule, it has one less number of electron to fulfill the total 18 valence electron. So it is more or less like an unstable species. But when it's readily react to sodium, it goes to Na, so VSO whole 6. So NaVOCO whole 6, this is the VCO whole 6 minus. So here total electron is a 6 plus 12. That means 18 electron. So NaVOCO whole 6 vanadium has total 18 electron. So it is more stable compared to the VOCO whole 6. So that's why VOCO whole 6 reacts readily with the sodium to fulfill this 18 electron in the valence bond. So it will be more or less stable compared to the VOCO whole 6. The last question is so select the best choice in which the following briefly justify the reason for your choice. Complex with the shortest CO bond length, NiCO whole 4, COCO whole 4, FeCO whole 4 2 minus. So Ni electronic configuration is 4s2 3d8. Total electron count is equal to 10 plus 8. That means 18 electron. And for cobalt CO whole 4 minus, total electron count is cobalt is 4s2 3d7. So 9 plus 8 plus 1 is equal to 18 electron. And for FeCO whole 4 2 minus, Fe is 4s2 3d6. This means 8 plus 8 plus 2, total 18 electron. So here all the three complex has 18 electron in the valence electron. So, but for the case of so CO bond length will depend on the electron density on the metal center. Which metal has more electron density, that will favor more back bonding, back bonding to the metal pi star orbital of the carbonyl, and that will decrease the bond order, and that will increase the CO bond length. So all these complex, nickel CO whole 4 is a neutral complex, CO whole 4 minus is a negative complex, 1 electron negative, and FeCO whole 4 2 minus has 2 negative charge. So for the FeCO whole 4 2 minus, total electron density is higher for the FeCO whole 4 2 minus. So here the more back bonding compared to the other three. So here the CO bond order will decrease more, so CO bond length will increase. But for the nickel CO whole 4, there is no such back bonding compared to the other these two, so it is a neutral complex. So here not that much extent of back bonding is happened, so it CO bond order is be higher, and it will have shortest CO bond length. So here Ni CO whole 4 has shortest bond CO bond length due to lack of back donation. Thank you.